Welcome to the Broadcast Dialogue Podcast, the show all about the media industry in Canada.
Broadcast antenna environments vary tremendously. In this sponsored segment of Broadcast Dialogue, the podcast, David Rusch is joined by Steve Moreen of Dielectric to take a look at 3 FM antenna projects where solutions were provided for unique situations.
All right, Steve, we'll get into the FM antenna projects here shortly that we're featuring today. We did touch on these in a written article for Broadcast Dialogue recently. But first, in a minute here, give us a brief overview of Dielectric.
Well, David, thanks for allowing me to be here with you. And I love talking about FM antennas and about Dielectric. You know, the story I understand is that the founder of Dielectric, a fellow named Doc Brown, started making transmission line for early World War II radar systems during the war. And after that ended, it was kind of a natural progression to start building products for early television and radio stations, FM stations, as they were coming online. So I think Dielectric built quite a few of the products that RCA Broadcast sold. And then in 1989, when GE sold the RCA Broadcast antenna division, Dielectric bought the antenna division and took over the products and improved the products. And then in 2000, when the Harris Corporation sold the Harris Antenna Broadcast antenna division, took over those products and have improved those products. So our portfolio is pretty broad. It consists of not only our own products and the RCA products and Harris products and things that we've developed along the way. So we make television antennas, radio antennas, transmission line, all sorts of RF, high-powered RF filters and combiners. We also make lots of transmission line. Actually, for the TV repack, we made over 111 miles of high-powered television transmission line.
Oh, that's a lot. Well, let's get into some of these FM antenna projects. And first situation we're going to look at, it's a 3-kilowatt university radio station with the FM broadcast antenna on its student union building. The station wants to reduce the RF radiation on the building's rooftop. They want to improve reception by reducing the signal's multipath and improve program audio quality. Steve, how do you handle that?
Well, this was a typical situation. Let's face it, most stations buy their FM antenna, put it up and forget it, and that FM antenna can have any number of generations of transmitters because they generally work well and they're very reliable. But the problem is sometimes they're not really appropriate for the situation. This antenna, which was installed about 30 years ago, was a full wavelength spaced antenna. It had 3 transmitting elements. And the good thing about that kind of design is you get quite a bit of antenna gain. You'll get a power gain of 1.5 out of an antenna configured like that. The bad thing about that antenna, full wave spacing, it's got such a big fat lobe or beam width vertically that it puts a lot of radiation right on the ground below the tower at the tower base. And in this case, since it was on a relatively short tower on a 5-story building, it put a lot of RF on the rooftop, which the customer didn't want to have. So we wound up designing a 3-bay single station antenna, DCR H3. We half wavelength spaced the elements, and at this spacing, there is the minimum amount of power at the base of the tower. And so that eliminated the RF problem on the roof of the antenna. But the other benefits were, because this antenna is broadband, the station was able to hear high frequency response and reduce the injection of their subcarrier substantially. So the engineer called me up afterwards and said, I didn't realize an antenna could make that big of a difference in how a station sounds. And he also said to me, this antenna is amazing because people hear us in places they couldn't hear us before, or in places that were noisy, they couldn't get the signal very well. And that's, we think, because essentially this antenna has excellent circularity, or a very, very good axial ratio between the horizontal and vertical element of the transmitted signal. So it was a real win for the station in replacing their antenna.
Steve Moreen with us from Dielectric. Okay, Steve, here's our second situation regarding broadcast antenna projects. As you probably know, tower space to support FM antennas is becoming more scarce and expensive. We got a major market broadcaster wanted to replace a single station auxiliary antenna with a 2-station antenna using the same space on the tower. And by the way, the antenna will be close to the ground on a shorter tower, so the potential for an RF radiation hazard is a concern. So Steve, how do you handle this?
Well, this is a variation on the first case. This was in the San Francisco Bay Area on a relatively short tower, maybe 100-foot, 200-foot tower with a lot of antennas. So there was a real concern about the amount of RF radiation on the ground underneath the tower. And there was a concern about putting 2 stations into this single station antenna. The single station antenna was originally a 2-element full wave spaced antenna with a power gain of 1. And what we decided to do was use our DCR-M3. The DCR-M radiating element is a broadband radiating element. And so it allowed us to basically service the 2 stations that were about 5.5 megahertz apart and still provide a very good VSWR of less than 1 to 1.05. In order to get the maximum signal out of this antenna system, we chose to space the bays at 0.66 wavelengths. Now, there's this magic formula. It's called n-1 over n, where n, now listen, there'll be a quiz on this, n basically is the number of elements, radiating elements, minus 1 over n, and that particular formula determines when there will be a null at the ground below the antenna. So n-1 over n is 0.66. When you have a 3-bay antenna, we basically space these antennas at 0.66 wavelength, and instead of having a power gain of 1, we had a power gain of 1.23. So this antenna was 23% more efficient than the 3-bay half-wave spaced antenna that we could have put in, and it was 23% more efficient than the full wavelength spaced antenna that was originally at the site.
Okay, excellent. Steve Moreen, Regional Sales Manager for Dielectric, longtime radio and television equipment manufacturer based in Maine. And that borders Canada, of course. And if you go to St. Andrews by the Sea, beautiful place in Canada bordering Maine. I loved it there. Great town. Never been, go. Let's go to our third FM antenna project situation here. Steve, there are generally 2 classifications of FM broadcast facilities, full power and low power. So give us a little more information about the difference and an example of a unique product Dielectric intended for the low power broadcaster.
Well, most regulatory bodies basically have special rules for FM translators and FM boosters. They're considered to be normally low power augmentation facilities to the full power stations that the FCC also and generally authorize. And because they're smaller stations, they have a different set of rules, which makes it easier for them to exist in the general infrastructure of all the big stations. Generally, you would find an FM translator or an FM booster on a hill overlooking a community that does not have line of sight to the broadcast stations, tucked in a valley somewhere. And there would be a receiver on the hilltop, and then there would be a low power transmitter, and there would be a directional antenna. Normally, inexpensive directional antennas such as Udo Yagis or log periodics are used, and they work quite well in these applications, except they have an inherent beam width in their axial or horizontal pattern of only 30 or 40, maybe 50 degrees at the most. And that was a problem in this case because the FCC consultant wanted to put an antenna on a roof. He wanted to have a very broad radiation pattern in the horizontal direction, 270 degrees, and he wanted a really tight null to the back of the antenna to prevent the signal from interfering with another station. It would have been very difficult to do with a log periodic array or a Yagi array. So our engineers looked at it and said, guess what? We can take two DCRT antennas. There are least expensive and they're designed for low power and medium power stations. We will space them at 1/2 wavelength and we will push the lower antenna out 30 inches from the top antenna. And when you take the azimuth pattern of these two antennas together, you get a cardioid on the front side of the antenna that's about 270 degrees in the azimuth around the front of the antenna, and you get a deep null to the back. So it was an easy way to easy and simple way, no parasitics, no reflectors. It was an easy and simple way to provide the antenna pattern that the customer required for his FCC license. So I guess what I like to say to you in wrapping up, don't overlook the antenna. If you're redoing a facility or building a new facility, it's often easy to spend a lot of time on the studio equipment and the transmitter. And after all, the antenna's up there, nobody really sees it once you put it in. But it's very, very important to consider the transmitter and the antenna. The antenna is a very important component. Consider things like radiation hazard, the beam width of the antenna, the ability of the antenna to operate truly as a circularly polarized antenna. And the other thing I'd say is don't forget efficiencies. Being able to put two stations on one antenna is a great way to help the bottom line.
That's Steve Moreen from Dielectric. Learn more at dielectric.com.
Thanks for listening to Broadcast Dialogue. For more information about the podcast or to receive exclusive access to our weekly briefing about the Canadian media industry, visit us at broadcastdialogue.com. Don't forget to like us on Facebook, connect with us on LinkedIn, and follow us on Twitter and SoundCloud.